Welcome, everyone. This is the Quimper Geological Society lecture. Today is May 3rd, 2025. I'm Carol Serdar-Tepper, and I just want to welcome you and thank you for attending today's lecture. And we also give thanks to the First Peoples Nations that were great stewards of the land. Directly after today's talk, we'll be going down to the poorhouse to have a libation with the speakers and thank them. If you would like to join, please do so directly after the talk today. And then, let's see, this is the last 2024-25 lecture, and we will be starting up again in September with Tom Badger on September 13th, which is a Saturday, and he will be talking about Highway 112 and on the North Olympic Peninsula and the challenges with keeping the highway safe. We'll also be hosting, currently we have David Williams coming to talk about his 2 new books that he's published, and December 6th, and then probably May, Nick Zentner will return to Port Townsend or Chimacum. Not sure where we're going to host that yet, but last time we had a lot of people that showed up for that. So we hope that you can join us, and if you have any questions, take a look at the website, and hopefully you'll be able to get your answers met. And if not, we have a way for you to communicate with us if you have additional questions. Thank you. Now Ralph Dawes, an advisor, will be introducing.
When I was in grad school, same school that our 2 speakers have gone to, University of Washington. Oh yeah, get up in the video. Got to pay attention to what the director is signaling. Anyway, I met some fellow grad students had this habit of wherever they went, where there was a beach or a river where there was sand, they would collect a vial of sand. And I asked why, and they said, well, because there's so much information in sand. It tells you the environment, where you collected it, how the water was flowing, and it also tells you where the sand came from if you analyze it really closely. And I thought that was cool, so I thought I better pay more attention to the sand. And then more recently, long after grad school, Cheryl and I, my wife and I, were visiting the coast of the Olympic Peninsula. And when you're driving down there from the north, you come back out to the coast after driving inland a little bit, and you come to Ruby Beach, part of Olympic National Park. And I was going, Ruby Beach? Why do they call it Ruby Beach? And so we got out and looked, and I did have my hand lens because of the training from my grad student friends. But we took a look at the sand, and it was full of, parts of it were full of garnet. And the problem is, this is out on the west coast of the Olympic Peninsula, and in my understanding, there wasn't any garnet on the Olympic Peninsula in the bedrock. So that was a puzzle. So then, a year ago, I was at the Geological Society meeting in Spokane, and I saw that there was a poster presentation on garnet in beach sands of Puget Sound and the Olympic Peninsula. So that was exciting. And I went and met Leigh Tucker and Marquis Richardson, and they were so energetic and articulate, which was exciting to me to, in itself. I started thinking of recruiting them to give a talk at that point. But anyway, and I heard about their research on this garnet in some sands, some beaches of the Puget Sound and the Olympic Peninsula all the way out to the coast, which is a problem. And they were working on it. So with pleasure, I present to you Leigh and Marquis to tell us about these beach sands in our area. Next time you're out on the beach, pay attention to the sand.
Hello, everyone, and thank you for inviting us and allowing us to share the research that we've been working on as undergraduates at the University of Washington. I graduated my bachelor's back in 2023, and Leigh will be graduating this June with her bachelor's. So she's, give a round of applause for that. So yeah, we just wanted to talk to you today about these amazing red, pink, purple kind of garnet sands that we see out here on the beaches. We investigated both the Olympic coast and the Puget Sound garnets, and we just want to share with you today some of what we've learned through that process.
You have the clicker. There you go. As you heard, my name is Leigh Tucker. I am excited to graduate in a couple of weeks, but I'm also really thankful and appreciative and excited to be here today because it's not very common for undergraduates to have the opportunity to do independent research, let alone be able to come and talk to an organization like this about their research. So this is an awesome opportunity you have given us. So thank you very much. And we'd also like to take a moment to acknowledge our mentors who helped us with this research. First, Dr. Elizabeth Davis for help with fieldwork, Dr. Kaylee Condit and the Structural Petrology and Lithosphere Group at the University of Washington for funding both of our projects, Dr. Will Hoover for being our mentor and advisee on the petrological analysis, and Dr. Juliette Kreider for her overall mentorship.
All right, I wanted to start off this presentation by showing this amazing image. This was taken by Jeff Williams, an astronaut, about 10 years ago while he was aboard the International Space Station. And so just to orient ourselves, we're looking at the peninsula from the west, from over the Pacific, and north is to the left there. And we are up here in Port Townsend. And so I think this image is, one, it's just beautiful, and it just shows just the beauty of the region as a whole. And this region has been impacted by multiple geologic processes in geologic history. And to talk about some of those, the first is the Cascadia subduction zone. So off to the west, we have the Juan de Fuca plate that is being subducted underneath the North American plate. And this has created the Olympic accretionary wedge. And so about 50 million years ago is when the Olympic accretionary wedge began forming. We have the Silesia terrain, this basaltic terrain that was being subducted and accreted, and that's present over here. And then as subduction continued, we have oceanic sediments that are being accreted and continue growing the Olympic accretionary wedge into what we know as the Olympic Mountains out here in the peninsula. And we've also had many glacial advances and retreats in this region over the last several million years. The most recent was the Vashon state of the Fraser glaciation, with the extent of that reaching southward about 16,000 years ago. And that was a major erosional and depositional event that has impacted the geologic region or the geologic history of this region as well. And we have the Juan de Fuca lobe that came out here, and we've also had ice come down in the Puget lobe through the Puget Sound. And so today we want to talk about these small little garnet grains, some of these pink, kind of red, purple grains that we see over here in this picture, to try and get a better understanding of the story of the Olympic Peninsula, the geologic history, and how it's been impacted. And so for this, for my two sites that I investigated out on the coast, I had Rialto Beach, that is right up here on the northern location, and that's around La Push, and then we have Ruby Beach to the south near Oil City. And now Leigh is going to tell us about some of the garnet formation.
So many of you probably already know that when rocks are under certain pressure and temperature conditions, the minerals in them will start to transform into new minerals and therefore creating a new rock structure. And when the minerals that are being transformed contain elements like iron or magnesium or calcium and silica, then garnets can start to grow. And this is all through a process called metamorphism. Garnets are often considered a signature mineral within metamorphic rocks because they can grow under so many different pressure and temperature conditions. When the transforming minerals release those particular elements and they come together to start forming a garnet, they form in a tetrahedral or create a dodecahedral or trapezohedral shape, as can be seen in the image of the rock that we have up there. Now, if the pressure and temperature conditions change or the bulk composition of the rock around the garnet changes, then the new pieces of the garnet that are growing will be different from what's on the inside. And this can create what looks like a corona or a zone. Marcus likes to refer to them as tree rings. And they record that change in the bulk composition and or the pressure and temperature conditions. And as they're growing outward, they don't grow abruptly, they grow very slowly. And as they're growing, they will sometimes encircle and entrap a little piece of an untransformed part of that original rock that they're hosted in. And when that happens, it creates an inclusion. And the garnet is then acting like a protective shield around this inclusion so that future pressure and temperature conditions will no longer impact what happens to that host rock.
All right, so here is a pressure and temperature diagram. It showcases all the different metamorphic facies that exist across different pressure and temperature conditions. So like Leigh mentioned, garnet is a metamorphic mineral, and it's able to form in several of these different facies across multiple different pressure and temperature conditions. However, there are other minerals that will only form in certain facies and under certain pressure and temperature conditions, and these are what we call index minerals. And these can be trapped and included within the garnet as well as they're forming. And so the motivations for this work was, one, to see if I could use inclusions to investigate the tectonic setting of the garnet formation, to see if I could use the inclusions inside of the garnet rather than the garnet itself to try and learn more about the conditions that the garnet formed in. And then secondly, we just had some uncertainty about the provenance of these garnets, which just gave us kind of two overarching questions. Was where did the garnets come from? What's the host rock? Where are they originating from? And how did they get there? What was the transport mechanisms and methods of getting the garnet to where they're currently seen today? So my first hypothesis that I investigated was the subduction, geologic process and interaction. And so for the subduction zones, these are environments that have high pressure and low temperature conditions. That's kind of this blue line right over here in the blue schist and eclogite facies. And so within these facies, we can get index minerals that will form within those facies specifically, like glaucophane, like a type of sodic amphibole, lawsonite, and omphacite. And so for this hypothesis, we would have garnets and forming and these index minerals forming in this subduction zone where the Juan de Fuca is going underneath the North American plate. And then these minerals can be underplated or accreted to the bottom of the North American plate. I like to think of this as like peanut butter getting stuck to the roof of your mouth. And then over time, they become uplifted where they're exposed at the surface, and then they're eroded and transported down to the beaches via like fluvial processes. And then when they hit that lower energy environment, they're deposited out on the beach surfaces. And that's where, again, where we see them at Rialto and Ruby Beach. The second hypothesis that I was investigating was whether these garnets were influenced by glacial transport methods. So up to the north of us, we have the North Cascades, and we also have other mountain ranges within British Columbia, like the Central Coast Range, that have been impacted by regional metamorphism. And that is where we have both high temperature and high heat due to like burial and compressional tectonic forces. And this is right here, this green line, which shows regional metamorphism. And that's where we get the green schist and the amphibolite facies. And some of the index minerals that we see within that are staurolite, sillimanite, biotite, albite, and actinolite. And so for this story, we would get those minerals that would be forming along with the garnet and trapping them up in this coastal range or North Cascades. And then they would be brought down southward with the advance of the glaciers. And then they could be transported out the strait along with the Juan de Fuca lobe and then deposited on the beach. One constraint with this hypothesis is that let me backtrack. Constraint with this hypothesis is we don't, like Ralph mentioned earlier, we don't have widespread high-grade metamorphic rock within the Olympics to produce the quantity of garnets that we see out on the beach. Instead, we have a low-grade metamorphic rock that's found within the Olympics. Constraint for this hypothesis is that the extent of the glaciers was found to be north of Ruby Beach. And although we have seasonal current patterns that are able to bring sediment southward, we see a general overall longshore drift pattern that's moving sediments northward up the beach, potentially limiting garnets from being transported down south to Ruby Beach. Now I want to walk you through some of the methods and some of the challenges and fun things we got to do for this project. So first off was, again, here's these garnets here. You can see them streaking there, and these red patterns there, and also these kind of lighter pink ones here within this stream bed. So the first part of this project was locating garnet sands to collect. So for me, my site locations were pretty easy. I was helping Elizabeth Davis do field work out at Rialto Beach, where we saw some garnets already, so that was easy. And then Ruby Beach, not rubies, but garnets were present there. It's got its name. So I went out there and I was able to collect samples for both of those two locations. One kind of challenge is that the garnets aren't always present at their locations. As waves come, as sediment moves, sometimes they become buried. Sometimes you don't see them. And other times you go out to the beaches and you see, nice wide swaths of it like this. And then on the beach sites themselves, you often find them within two kind of specific locations. You see them near a high tide line like we see over here. And so as the waves advance and retreat on the beaches, the garnets are more dense, and so they'll drop out into these kind of streaks or winnowing pattern that's in the parallel to the direction of the wave pattern. And then we also find them within small stream beds along the beach. And so as the garnets, or as the sand is being moved by the stream, the less dense material is being picked up and transported out, and then we get the more dense material accumulating together, kind of like placer gold deposits, things like that you'd see in riverbeds. The next step is garnet collection. So the garnets themselves are really fine grained, and so we'll find them in areas where they're in fine grained sand sediment collections, and they form in real thin lenses or layers on top of the beach surface, which can make it a little bit difficult to collect them. So we use this cool Nigiri Gama, it's a hand hoe, and we tried to carefully scrape off the top sediment, but again, we still get a lot of the underlying sediment that comes with it. So that leads us to trying to separate that garnet out further so that it's collected together for our samples. I originally tried using a method similar to gold panning, where I dumped the sand into a pan in a big bowl of water and swirled it around, trying to get them to collect, and it failed miserably. So after some further talk with my advisors, we decided to dry out the sands, put them in sieve stacks and shake them, and use a France magnetic separator to separate the garnets. Now, this is a machine that is able to separate sediments or material based off of their magnetic properties. And so this should be a video that will work here. Awesome.
Oh,
okay, I'll talk over this. So what we do is we dump the sample down through this funnel, and it falls down onto the slide that's angled both down to the left and slightly towards us. And so it runs under this magnet that we have set to a certain magnetic specification, and anything that's less magnetic will fall towards us, and anything that's able to be held up by the magnet is retained in the backslide. And then they're both transported down and dumped into the two different tins there at the end, with the more magnetic stuff up top and the less magnetic stuff down on the bottom there. All right. And so after I played around with that for a long time, trying to get all the settings correct and dealing with lots of magnetite sands gumming up the machine, I got a way better separation of the garnets here, as you can see in this file here, and then over here. So this is kind of what we ended up with. We would get the less magnetic stuff sorted out into one bag, the more magnetic stuff in another, and then the garnets themselves in that central bag. So then we were able to take these and mail them off to be made into thin sections. And so they take our samples of sand, they epoxy them together, and then they sand it down into this thin section. And then we take that and we put it in a fancy scanning electron microscope to run a scanning electron microscopy energy dispersive X-ray spectroscopy analysis on those. And so what you see here is, so we put that slide within that machine, And then what I did was I had a digital image created of that slide, and then I went through and randomly selected grains that I wanted to analyze and placed boxes around those. And so as you can see, that is zooming in on one specific grain that I analyzed over here. And here is one individual grain of garnet that I was analyzing. And as you can see, these kind of black splotches and some of these other splotches within are actually inclusions themselves that are contained within the garnet grain. And that's what we were looking at specifically. And so I analyzed 57 grains of garnet across the two beaches. And I also had about 450 spectra or individual points that I analyzed. And what those are, with this machine, you're able to click wherever you would like on this, on the inclusions, on the garnet itself, and the machine is able to give you an elemental composition of that exact spot. And so from that, we get this spreadsheet of data, and it gives you the elemental weight percentage ratio of all the spots that you clicked on, essentially. And so, for example, like right here, we've got about a 50 to 50 ratio of silica and oxygen, which indicates a quartz mineral that was included within the garnet grain. And so this was definitely like the most stressful part of the project. I had about a week to run through and do 450 mineral identifications based off of elemental composition and get a poster together to present. So time constraints are definitely fun to work with. And my results, there were no distinctive subduction zone minerals that I found. There were no smoking guns that were indicating the subduction story. And instead, we found inclusions that were consistent with, but not limited to, regional metamorphism, like quartz, chlorite, albite, micas, things like that. And this is a chart that I created to compare the two beaches. And so what it shows is the mineral inclusion occurrence in the garnet grains by the beach. And so how you would read this, this dark blue is Rialto Beach and the light blue is Ruby Beach. And so looking at this quartz line here, 100%, so every single one of the garnet grains that I analyzed at Rialto Beach had one or more quartz inclusions within it, and 88% of them at Ruby Beach had quartz inclusions with it. And so that's how you would read this graph. And from this, you can see there was no significant difference in the inclusion types between Ruby and Rialto Beach samples. So they were pretty similar between the two beaches there. So my overall conclusion was that the garnets that we found out on the beaches were likely formed in regional metamorphic environments, in mountain building environments, likely up north in Canada, North Cascades, and then were transported down south to the beaches via glacial processes. Now, after doing this research, there's still some questions, and we decided we just wanted some more research to try and identify some of the potential source rock that could be contributing to the formation of these garnets. And that is where Leigh Tucker took on the next portion of this project.
So as the next year, as I was trying to figure out the topic for my honors research undergrad project, I recalled Marcus's work with the garnets from the coast, and that he had concluded that it was most likely transported to the coast, which I was like, that is so intriguing. How would that be working? And so I reached out to Marcus, and with the help of Juliet Kreider, we determined that the best next step would be to analyze this glacial transport method, the possibilities of that. And so that's how I got involved. That was my first motivation, is to see if we could figure out if the glacial theory had any merit to it. My second motivation for this is that this whole idea of using these garnet inclusions to help identify to use them as tracers for detrital sediment, which is just a really fancy way of saying to find the pathway to where the garnet sands originally came from. And the first time that this was ever used, that we were able to find in literature, was in 2018. So this is like a really, really new geological tool. And the work that Marcus and I would be doing would actually be able to add to the evidence that this is a legitimate tool for our use. So testing this glacial theory. So as Marcus had mentioned, the garnets could have formed up here in the coast mountains of British Columbia, and then come down through one or more of the Cordilleran lobes, specifically thinking of the Juan de Fuca, which would have come through, which we believe may have come through the Strait of Georgia and then out through the Strait of Juan de Fuca, and at the same time kind of coming over Vancouver Island. And also the Puget lobe, which is believed to have to have split off from the Juan de Fuca lobe and come south between the Olympics and the Cascades and carved out Puget Sound as we know it today. So initially you would think that the most likely, as Marcus had said, that the most likely option would have been the Juan de Fuca lobe because it actually came onto the peninsula and reached the coast. However, as Marcus also mentioned, the extent does not reach down to Ruby, and the longshore drift pattern is the wrong direction to get those garnets to Ruby Beach. So that lends itself to being like less likely. So then we decided to look at the Puget lobe, and the Puget lobe has also an issue of, well, it doesn't even reach the coast. So how would this work? So when you think about when the lobe or when the Cordilleran sheet receded, there needed to be a spillway for its drainage. And that could have come through the Chehalis River Valley. In fact, it is believed that that was one of the major spillways for those drainage waters. And the glacier till would have come through the drainage, through that spillway, and deposited within the valley. And today, as those glacial tills are being exposed, they could be finding a fluvial pathway to the coast, for example, through the Chehalis River. So there is a possibility, and then going north with that longshore drift. So it's got some possibilities. So our hypothesis is that if it is indeed if the Puget lobe is one of the places where there could be sourcing the garnets on the coast, then we would, if we look at the inclusion composition within garnet sands on the Puget Sound, in the Puget Sound, they would be correlative to those that are on the beach. Me finding sites was not as easy as Marcus. We knew that there were garnets at Manchester State Park because the University of Washington uses that as a field site every summer for their field camp. And every summer, most summers, students and instructors find garnets there. So we were able to collect at Manchester State Park, but then we were like, where else? So I reached out to the Department of Natural Resources. I reached out to the Washington State Geological Society, asking whoever I could think of where there might be sands in the Puget Sound. And they always referred me back to Ruby Beach. I was like, that's not in the Puget Sound. And I was getting really frustrated. And Marcus had a friend who was interning at the Department of Ecology. Never even thought to ask them. But she had heard rumors that there were garnet sands at Double Bluff on the south end of Whidbey Island. So Marcus and I and our friend, another geology undergrad at the University of Washington, had a field trip. And we went out to check out Double Bluff. Well, to get to Double Bluff, you have to walk along the beach of Useless Bay. And we found even more. It's like, this was so thick. It was like at least a half an inch thick of garnet sands. So you get to Double Bluff, there are garnet sands. So I sampled some of the ones at Double Bluff. We came back, got some at Useless Bay, found out Vigash had never he didn't even know about Deception Pass. So we decided to come home via Deception Pass and went to Deception Pass West Beach. And swath, Marcus used that word earlier. It's like the beach was covered in garnets. It was insane. There was so much of it. So I ended up with 4 sites. It was fantastic. So to keep our analysis and our comparison as close as good as we could possibly make it, I made sure to use the same processes that Marcus had used, with the exception of some things that made it a little more efficient. For example, with the Franz, because it gummed up so much for the magnetite for him, we hand removed as much of the magnetite with a hand magnet that we could before putting it through the franz. Actually have some of the sand in the back with a magnet so that you can kind of play around with it at the end if you wanted to. And so it went a little bit easier. We saved some time. I want to take a step aside for a moment. And this is one of those things to learn as a new scientist. Every scientist learns this at some point. There are things when you are doing research that you have absolutely no control over. For me, what happened is that once we had them separated and we sent them off to the company to be turned into slides, they got lost in transit. It was lovely. By the time that they were found, half of them had been broken because they were in these glass tubes. Luckily, there was at least one tube of each site, so I still was able to have samples from each site. But in the meantime, I was just doing a bunch more research and doing what I could to be prepared for when we finally got them. When we did get them, I also only had about a week before my first presentation. So when it came to the SEM EDS, we also sped things up a little bit. I did a different type of random selection, which just was a little bit faster than the way that Marcus did it. However, I wasted all of that time that we saved because I am somebody who gets a little bit overzealous. And whereas Marcus did a really great job of, okay, that inclusion looks like it's probably very similar, because when you're looking at these in the slides, it's pretty obvious where you get to, once you've looked at enough of them, you're like, okay, well, this is going to be quartz. And okay, this one's going to be apatite. But I was like, it looks like it could be quartz, but it might be something different. So I'm going to go ahead and get another spectrum of it. I had one grain that had over 50 sites, and that was a little bit overkill. Will, our advisor, said it wouldn't make any difference that I had so many more spectra on one grain. When we came down to the analysis, what it did do was it just ended up being a lot more work. I tested 20 garnets from each site, so I had 80 garnets. I had over 1,300 inclusions from those 30 garnets to be able to identify, and I ended up identifying 48 unique minerals. The next step that I did beyond what Marcus had done was I applied some machine learning methods to my analysis. Now, we didn't need to use machine learning because machine learning is just a way to utilize computing power to make things faster if you have a huge data set. Our data set wasn't so big that we needed to do that. However, it gave me practice on using these machine learning methods, and it also allowed for us to go just a little bit deeper because there were some analyses that we wouldn't have been able to do because we just didn't have the knowledge. So the first of these machine learning methods that I used is called a principal component analysis. It's also known as a PCA. What it does is it takes something that if you have so many variables, and in machine learning they call this dimensions, you have so many variables that when you're looking at something, you can't really know how to compare or contrast. So you reduce those numbers through this, or through these variables, through this PCA. One of the things you really have to make sure that because you're reducing, you're adding different variables together that are similar to each other. So you have to make sure that you are maintaining the integrity of your data. You have too much or too high, let me go back for a second. The way that you measure whether or not you have viable integrity is through a term called variance. If your variance is too high, then that means that you did not scale your data correctly, or that you only have one principal component. If it's too low, it means that you've lost too much data as you've reduced down those variables, and it means that your analysis is not going to be useful. There's no cut and dried thresholds for a PCA because it's all dependent upon the project that you're working on. But the powers that be, meaning the people who know a lot more about it than I do, say that a good range to have for a variance is between 60 and 80%. And we had right around the middle of that range. And the dimensions that we used for this PCA was the mineral oxide weight percentage for the inclusions. And we had about 45 or so of these mineral oxides. And so going from 45 down to 2 and keeping 70% did pretty darn good. This is each one of the garnets plotted with the two principal components. And you can see that the vast majority of them are all plotted like right on top of each other. There are a few outliers, but the majority of them are right on top of each other. And that is really positive because it helps us to know that seem to be doing things, that we're getting things that are very similar. Our two principal components, whether it was on the coast or whether it was in the sound, were silica and aluminum. Not really too much of a surprise for the silica at all. And then for the coast, the third principal component was titanium. And in the Puget Sound, it could have been, depending upon the site, either phosphorus or calcium. And so you'll also notice that there are these outliers. And almost all of these outliers are actually from the Puget Sound. Now, the combination of the fact that the third principal component and that the majority of the outliers are Puget Sound, that kind of gives a foreshadowing of some of the things that we found. But what I do want to, when we switched over to our new slides to present, we lost some of our formatting. So sorry that you cannot read this very well. But what I want to point out is that a PCA, at least the way that we used it, was not to give evidence for or against our hypothesis, but rather what it is it's verifying that it warrants further analysis. So this is a graph very similar to the one that Marcus had produced, where we're showing the percentage of garnets that had a particular type of inclusion in it. And the blue represents the coast, the pink represents the sound. And there's a good similarity on a lot of things, but there are a few that are really, really different, such as the alkali feldspar and the mica, but most especially the amphiboles and the zircons. There's just so much difference between the two regions. And we didn't really understand what might be causing that, so we wanted to look at each site individually. And I know this graph is very crowded, so hopefully my descriptions will be able to help explain it a little bit. So when we're looking at this amphibole and zircon again, what we notice is that it's only the light blue is Rialto. There's no dark blue for either one of them, which means that neither one of those minerals were found at Ruby Beach. And so that could be part of the reason why it was so much different between the sound and the coast, because there is just a big difference within the coast itself. One of the other elements that stood out with this graph is that we've discovered there's like kind of this pairing between different beaches. Obviously, the coast is pretty similar. We already learned that. But also these light pinks, which are Useless Bay and Double Bluff, which are right next to each other, are pretty darn similar. It's like they're following a pretty similar pattern. But then Deception Pass and Manchester Park, they are like the furthest away of all of our beaches within the sound, and they're also really similar to each other. And so it's like, even within regions, we were finding discrepancies, but then we were finding pairings as well. So it's like, we don't know enough. There's so many more directions that we can go with this study to try to figure out why this is happening. But we just thought it was interesting that we were finding both similarities and dissimilarities within the same region. And then really important is hidden kind of in this other column. The other represents all of the minerals that we found that are not listed specifically on this graph. And in this column, we found some sodic, or is listed some sodic amphiboles. And you may remember that Marcus was saying that he was looking for a smoking gun that would indicate subductive zone minerals. And not all sodic amphiboles, they can grow anywhere. I mean, sodic amphiboles are pretty much anywhere within a blue schist, green schist phasings, but some of them are only in a blue schist. And we did not have the ability with the level of our analysis to determine which sodic amphibole we found. But it's just very interesting that we found some in the Puget Sound, only in the Puget Sound.
All right, you can hold on to that. So while Leigh was doing her fancy machine learning stuff that she shared earlier, and she'll continue to share, that was way over my head at the time, I was doing some reasonability tests to look at the garnets themselves to help, add to the data that we were collecting. And so this is a ternary diagram that we created, and each one of these triangles here has 3 different end members of garnets that we're comparing to one another. And since there's 4 end members altogether, created 4 of these individual charts here. And so each one of the garnets that we investigated are plotted within their own triangle. And you can imagine this kind of folding up on itself into a pyramid, and each one of those plots or points would plot into like one point in 3D space essentially, but it's presented like this. And so as we were collecting our data on the inclusions and the elemental data from that, we were also clicking on the garnets, and that produced the elemental composition of that. And from the plotting on here, you can see that most of them were this iron-rich garnet, which is almandine. So the similarity between the Puget Sound and coast garnets kind of showed us 2 things. That one, there's a commonality in the garnets themselves, which is, compares to our results that we were finding that there is some similarity between the garnets in the Sound and in the coast. But it also is validating the work that we're doing, that looking at the inclusions, because as we've talked, there is some variance between the Puget Sound and the coast garnets. And you wouldn't see that if we were just looking at the garnet type themselves. So it really validates going in and getting more details about the inclusions themselves to try to add more to this story.
And then I wanted to look a little bit further deeper into possible source rocks. And to do that, I used the next form of machine learning that we decided to use, or that I decided to use. And it took me a little while to understand what a random forest was, so I would like to take a moment to help you guys all understand that, because it's not intuitive in my mind. So the way that a random forest works, it's a machine learning algorithm that uses decision trees. So think flowcharts. So this would be one tree. And what it does is it takes specific features of the data from a huge a pool of data, and it comes to a decision. And then it makes a whole bunch, it makes just a forest of these trees, and thus the name random forest. So, and then tested on another set of known data. And the more data that you have to be able to train with, the better your model will be. And one way to increase the randomness and increase the diversity of the trees within your forest, and also then to reduce overcorrelation, is to do a method called bootstrapping. And what bootstrapping does is it takes it, so once one particular type of data, so each one of these trees pulls in several pieces of data. And then bootstrapping would take all of those pieces back, put them back into that pool, so that all of the options for the pool can then be used in the future trees. So there's a good chance that some of that data that was in that first tree is going to be in a future tree. And that again helps to increase that randomness and create your forest. And when you're in a random forest, when you are trying to do a comparison, like I'm going to be doing, I'm trying to compare between these different, the garnets to a potential facies, then the random forest prediction, that final prediction will end up being the majority vote of all of the trees that were in the forest. So the model that I used is called Garnet RF. It's open source, which means that it is available free of charge for anyone to use. And it was designed in 2021 by Jan Schoberg and Schoenig and his team. And it was trained on over 13,000 garnets, which were then bootstrapped. So it was a huge data set. And it was the specific features that are in that pool are the 8 most commonly analyzed oxides within a garnet. And the results of their of this Garnet RF forest model is 84 to 95% accuracy, which is really great. And of course, this percentage of accuracy is dependent upon what the facies is that is being looked at. Because metamorphic facies are the most complex, of course, it is the one that's on the lower end of that accuracy rating of 84%. So these are our results. This orangish yellow bar represents amphibolites, which indicate, again, mountain, most likely regional mountain building. And then the green, green, I cannot talk today. The blue bars represent a combination of blue schist and green schist facies, which is not helpful for us because we're trying to determine whether our garnets are blue schist or green schist. However, when we combine this information with our inclusion data information, we now infer that these bars are representing facies that are that fit in with a more of a green schist facies than a blue schist. And then finally, so like about 75% of them are amphibolite, 15%, about 15% are green schist, and the rest of them are either super high pressure eclogite or, interestingly enough, igneous settings, because garnets can form in igneous settings. Which brings us to this really interesting red bar right here at Ruby, and only at Ruby. 10% of the garnets at Ruby are consistent with an igneous setting, which is very intriguing because that's like, where the heck are those coming from? So more questions, which is one of the cool things about research, is that the more answers you get, the more questions you have. So our general conclusions are that they're probably regional metamorphic, or that the metamorphic rocks are probably, I cannot talk right now, because we did not find any subduction zone index minerals. The garnets on the coast are probably regional metamorphic origin. And the dissimilarity between the coast, the elements of dissimilarity between the coast and the fact that the Puget Sound had more mineral types in their inclusions and that there were sodic amphiboles in the Puget Sound means that the garnet, we are interpreting as that the Puget Sound garnets are just a little bit more complex and that there may be more modern sources for the garnets that are in the Puget Sound than there are for the coast. And yet there's a lot of similarities. And so this indicates that there's probably at least a partially shared provenance for the coast garnets and the Puget Sound. And then finally, our work has given validation, especially when you look at how we were able to take the random forest data and add to it, and the bulk composition garnet data, and add to it the inclusion data to learn more information about the garnets themselves. And so we have validated and added evidence to this new geologic tool.
All right, so some of the next steps for this project, we kind of have, again, those two overarching questions of where did the rock come from and how did it get to where it's currently at today? And so for this transport pathway, understanding how it got to the coast, next step will be, locating. I already got started on that because I will always take a road trip around the peninsula when given the opportunity. So I went out, I think it was last May, and so I went down and out to the Columbia, up to Long Beach, up the coast. I found dark mineral sands down here. I did not see any garnet sands within those sediments there. However, north of there, starting at the mouth of the Chehalis and northward, I was able to visually identify collections of garnet sands on the beaches there. And all the way up, see here in the Dungeness Spit out in Port Angeles, I also found some garnet sands there. And today, Leigh and I, we went out to Fort Worden State Park. I think it's North Beach out there. And I was actually out there 2 weeks ago and didn't see anything out there, but again, they're mobile sands.
But today
tons of them. They're all out there.
There were garnet sands all over the place today.
Yeah, so if you have the opportunity to go check that out after today, if you haven't seen them before, they're definitely out there today. And then, yeah, you want to take the next step?
Sure. And so from my tangent or my pathway for this of trying to identify the source rock, it's not quite as fun as what Marcus gets to do, but it would be the next step would be doing literature review, trying to identify where there might be garnet-bearing rocks within the North Cascades and the Coast Mountains, and then trying to locate which of those might match the lithologies that we discovered in the random forest model. And then once that has happened, to actually then get to go have a really fun trip and try to see if we can find those garnets and do a comparison there as well.
Yeah. All right. Thank you, guys.
Thank you for your attention. Thank you for inviting us. And do you have any questions?
Yeah, pass that around.
I'll bring my phone to whoever has questions.
You go for it.
All right, he was asking what the comparative density of the garnet sands are compared to the sands that surround it.
I don't know that we looked into it.
I don't know. We know that the garnets are more dense, and they accumulate with other like denser minerals like magnetite and things like that. And so, but comparatively, I'm not too sure. They're more dense than other sands that we're seeing out on the beaches.
This was 40 years ago. I used to run into a lot of garnet. I believe it was 1-4. Have you ever looked for the garnets up there and done any comparisons?
No, but that's a great place for us to look in the future. Yeah. We'll have to remember that. We're hoping to find another undergrad student to be able to take on some of these next steps because it's been a great opportunity for us as undergrads, and Juliet is already hoping and cheering on for finding more grad students to be able to do the next step, and so we can suggest that. Thank you.
That gets to my question, which is when the Cordilleran ice sheet was not in Puget Sound, when it pulled back north far enough, there was river drainage, and on Whidbey Island, mixed in with the glacial sediment. So the same bluffs as some of the glacial sediments. You've heard this. There are possible bars and just fluvial outwash coming from the Skagit or the Stillaguamish or above. So that's part of what you're talking about. There's more complexity in sand stuff. Part of it mentioned here as well.
Yeah.
So, yeah, the question was, we saw the sands today at Fort Worden. We didn't see it I didn't see it previously and saw it today. And whether that's sands were deposited there, and transported there, similar to the processes you were seeing there, or if they're being exposed currently. Regarding that, so yeah, again, like when I was out there 2 weeks ago, it was closer to higher tide. Sands moving, they can be buried. And then from my understanding, there, gorgeous bluffs out there of sand, and those are, outwash deposits from the glaciers as well. So my understanding is that they can be, currently being deposited sloughed off out of the sands, and then they're being sorted by the waves there on the beach. Yeah.
So we think that it's probably both, but up here on the north end of the peninsula, it's likely coming from the bluff, but there aren't garnet-bearing bluffs at Ruby Beach and Rialto. And so along the coast, it's probably being transported. That's what our thoughts are right now.
You implied this, but I just want a little more clarity.
Yeah.
The natural process of the sediment transport, ultimately the swash and transport on the beaches concentrates the garnet, mainly because of density, maybe also because of the shapes in the form.
Do you want to repeat that for the purpose of the video? It's the natural processes that are sorting the sands because of the density difference between like the quartz sands and the density of the garnet sands and the other heavier, like the magnetite and the other gem.
Yeah.
You folks obviously are very experienced going to a beach and looking at the sands and telling whether there's a garnet in it. What's your visual criteria for, oh, this beach is a right beach for garnets, or this one doesn't have any? How would I tell if I had a handful of sand? How would I visually determine whether there were garnets in it?
Yeah, so the question was, how would the average everyday person be able to go out and see or be able to identify where the garnets are? Or
not that he's an average or everyday person, but just
that there are garnets present on a beach. And so from the reason, just being out and looking at them all, the garnets themselves are really fine grained. So you'll usually find them in patches where there's lots of fine grained small sands all together. And then they're usually a real distinctive contrast in the color of the sand. They're usually in patches where you'll see a lot of black or darker sands, just because those are the more dense materials. And yeah, they're a little bit further up on near the high tide line. And so yeah, I'm guessing maybe when the tide's out lower and you've had a high tide event happening, you'll find them accumulated together up near there.
So harking back to the original question about density, so there must be some density difference if they separate out naturally by density.
For sure, yeah.
The density numbers are out there.
Yeah, exactly. Yeah, we can.
They're easily looked up.
Yes, yes.
So something that Marcus, when we were first talking about this, and he was describing to me how to be able to identify them, he talked about gem sands.
Yeah.
Yeah, and so is that this density?
This is a term of.
I know, but what it
Like
describing
garnet,
this as?
epidote, magnetite. Those are more dense minerals that will accumulate together, and they're found within these outwash sands as well. Yeah.
When you see pink in the sand, you then apply a hand lens to kind of verify?
Typically, yeah. I feel like most of those, the pink and reds are typically all the garnets that we're seeing out there. Maybe some feldspar, but it's usually pretty distinctive color.
And we usually have a hand lens with us.
Yeah. Yeah, that's nice.
I didn't mean to imply
No. Yeah. I was just saying, it's like, as excited undergrad students, it's like you get your hand lens and you kind of take it everywhere. I have it like literally attached to my hiking backpack so that I can we're up in the Cascades and I'm like, ooh, what is this? It's like I get it out all the time.
I don't have a question, I have a comment. I'm disappointed that you didn't find garnets in southern Oregon because there are beaches around Goose Bay that have garnet plasters that were every bit like Ruby Beach.
Oh, really?
And I've collected some very rich samples there. I'd be happy to share well-documented samples with you on maybe the coordinates and you can go visit them yourself. And there you can have a third hypothesis because when they're south, you have the Klamath Mountains that have consistent equivalent rocks with blue schist and things like that. And I've seen block of fame not as inclusions, but as a single grain from there. So might be an interesting continuation of your study. So I enjoyed the presentations. These were fantastic. Thank you.
Thank you.
So what he was talking about is that there are also garnet sands in Oregon that do include evidence of subduction zone metamorphism that would be a good comparison to be able to use with our grains up here. And something that I had learned as I was researching garnet sands, specifically what I was trying to do was try to find a good picture of garnet sands. They're everywhere. Apparently in New York and New Jersey, there are these amazing sands that are like super thick and the beaches look red. And so there's garnet sands everywhere. They're really fascinating and amazing beaches.
That's great. I thought it was great talk also. I think we all did. Any other questions? Well, then one more round of applause, please.